Hello, everyone. We're going to start talking about section 11.4, but we're going to do this in a couple of videos because there's a lot going on here. So the first video will be express concentrations of solution components using mole fraction and molality. You'll notice I haven't said the name of this section yet, and that's because I think this first topic can be discussed apart from the larger idea of colligative properties. So we're going to skip ahead to these descriptions, and we'll come back and discuss the introduction in a later video. So you might remember that we have throughout the semester been using something called molarity, molarity. So again, it's right here, molarity, as a measure of concentration, where that is measured as moles of solute per liter of solution. This definition works very well for things like stoichiometric calculations, where you're looking at focusing on the mole concept, and where measuring liter of solution is a fairly straightforward thing to do. It turns out for some of the things we'll be looking at in this section, molarity is not the best way of measuring concentration. So we'll be introducing two other ones. This first one we actually saw a little bit about in the section on gases when we were looking at mixtures of gases. So that's one place we see this one. We can also use this for solution properties. So mole fraction is defined as moles of a particular component of the mixture that we care about, divided by the total moles of all the components within the mixture. So we would use the symbol X to represent mole fraction, and then the subscript A is referring to which of the components of that mixture we're concerned with. So moles of one thing divided by all of the moles of all of the things. Okay, so that's mole fraction. The other measure of concentration we'll be looking at is called molality. Remember when I was talking about molarity, I was emphasizing the spelling of it. Molality and molarity have a very small difference in their spelling, so there's two L's in molality. And it's a similar concept to molarity. In fact, for very dilute solutions, they turn out to be identical. But for non-dilute solutions, they are not identical. Molality is defined as the moles of solute per kilogram of solvent. Moles of solute per kilogram of solvent. One of the reasons why we would have this different definition for concentration is because it turns out that volumes can change as temperatures change. So if we have a situation where we have changing temperatures, molarity doesn't work very well, where molality does work very well, because the amounts, things like moles and kilograms, are measuring amounts, do not change with temperature, whereas the volume does. And as we'll see later in this section, we will often be using this in cases where we are having a change in temperature. Molality we abbreviate with kind of a lowercase italicized m, whereas molarity we had abbreviated with an uppercase m. So just be aware of those distinctions, be aware of the differences between their units. When we are doing problems where we are changing from one measure of concentration to another, or we're given information to find a certain value, certain measure of concentration, you want to be very, very aware of what the units are. So that big M is moles solute per liter of solution, little m is moles solute per kilogram of solvent, because the units will determine which method you use to solve those types of problems. So there are several examples here in your book. I would like to kind of walk through one of them together, and then I will let you look at the others on your own and do some homework on this on your own. So this is one of the, definitely for this module, is sort of the high point in terms of calculations as opposed to concepts. So I want to give a little bit of space for you in terms of getting some practice with that, which is why part of why we're breaking this section into a few videos. So let's go ahead and look at this example. The antifreeze in most automobile radiators is a mixture of equal volumes of ethylene glycol and water, with minor amounts of other additives that prevent corrosion. What are A, the mole fraction, and B, molality of ethylene glycol in a solution prepared from 2.22 times 10 to the third grams of ethylene glycol and 2.0 times 10 to the third grams of water, which we're saying is approximately 2 liters of glycol and 2 liters of water. So that's, when you mix the 50-50, that's what you get. And we'll see later in this section why this is a perfect thing to talk about with what this section is about. So for part A, we want mole fraction. So for mole fraction, we need to know the moles of everything that is present. So in this, we are given the masses, and so we need to do conversions from mass to mole for both ethylene glycol and water. Okay, so you're given the formula here of ethylene glycol. I would not expect you to know that, right? I would have to give you that formula if you had a question like this. Water, you should know the formula for water by now, and so you'll need to do that calculation. So here we're showing that. So we're showing the moles of the ethylene glycol, the molar mass, so we're converting from mass to moles for ethylene glycol, and then the same thing for water, from mass to moles for water. These are not new ideas. These are things you should be able to do. What's new here is using that with mole fraction. So we then are looking for the mole fraction of ethylene glycol, so we have that number on top, and then we add both of them together to get the total moles on the bottom, and then we have top divided by bottom, and we get this number. When you're finding mole fraction, just kind of a hint here, it should always be a number between 0 and 1. There's never a case where it would be more than 1. It is a dimensionless property because it is a ratio mole to mole. So just be aware of a few things there. So that's part A. Let's discuss part B. So for part B, we're looking for the molality. So for molality again is defined moles of solute per kilogram of solvent. We have already found the moles of solvent in the first part, right? So that's this right here. For kilograms of solvent, we are given the mass of water in grams, so we just convert that to kilograms. So here we're showing that calculation again for moles of ethylene glycol. It's the same thing that was done above, and then here we're converting to kilograms, so it's just 2 kilograms. So then for the molality, we would take moles divided by mass, and we get a molality of 17.9 molal solution. So that's a really high concentration. So a couple examples there, and then another one you can check of a similar nature if you would like to, and then 2 more examples that are additional. They're not the same thing where you're doing exactly the same kind of conversion. In some of these, you'll be given one measure of concentration and converting to another. So you definitely need to be comfortable with these kinds of calculations. You will see something like some of these on the exam. So please take some time, go through additional examples, do some worksheet problems related to this, do some homework related to this before moving on to the next video.